Good morning. Let's take a look at lesson 5.4. Now, as we've been marching through chapter 5, we are now going to come to the last chapter in this segment. So let me go open up here. Let me get to the correct class. So if you were just joining, you get into your Google Classroom, you go to classwork. We are looking at lesson 5.4. Now, don't be surprised if you see in the future, if you're not listening to this live, a chapter 5 applications or a chapter 4 and 5 applications, because I have another lesson that I just realized that I used to do as a bonus. So this school year, as I record this, is in the year COVID and our calendar's off. But normally on a normal school year, we're doing chapter 5 right before spring break. And I do leave an applications assignment for students for bonus work, whatever else that helps them understand. So don't be surprised if you look up and maybe here over this Easter weekend, you see that there's an extra lesson added. But for right now, it appears to be the last lesson that we're doing over chapter 5. So let's go ahead and open that one up. And we'll see as we go along what we need. But I do know this. If you're listening to me live, you're taking care of number 1, attending class. I will put this on the YouTube lesson later on, but these are the 2 preferable ways of attending class, either through Zoom or here in person. Fill out the attendance link, which is also shown right here on this side of the screen. And then open up your bell ringers. Now, we'll need a formula chart for this. Let me copy this. I'm going to add it right in here. So some things I'm going to open up. We'll see as we go along what all we need, but I'm pretty certain we're going to need that formula chart and the Desmos calculators. Pretty certain of that. So I'll open those 2 up. This unit circle, as we go, you can click it and open it up, but I have a different one. I'm just going to pull onto, as you can see right here, this image. I'm going to pull it onto my notebook file as we go. So you can open that up if you like. With that, let's go start our problems over here. So number 1, we were reviewing this last class, and what we finally got to do is last class, when solving with trigonometry, we learned over chapter 5 that you can simplify crazy trig functions using spot oil. But what we did last class is we tied it back and said, okay, so now let's get back to a normal algebra situation where we're trying to solve a problem, but now we can solve the problems if trigonometry is mixed in between. So it doesn't have to be just for trigonometry is not just for solving triangles. We can also solve it using algebraic equations as well. So what do? Well, normal algebra rules apply here. You just kind of treat the trig function as an x itself. So the idea here is to solve 2x plus square root 3 equals 0 up until, so we're going to act like we're going to solve this same exact steps up until right after, when we get to where this would be x equals something, over here it's going to be sine x equals something, and we'll add 1 extra step. So this is basically normal algebra 1. So how would I solve this in algebra 1 is I would first subtract the square root of 3. And so I'll do that same thing here. I subtract square root of 3 from both sides of this equation. This is because x is only to 1 power. And so if it's only to 1 power, you can isolate by doing opposites here. Okay, so I have this set up. And I notice that 2 is multiplying times sine x, just as I had like a 2 multiplying by x up here. And so the opposite of multiplication would be division. And so we have sine x equals negative square root of 3 over 2. Now, notice what I wrote up here. That would produce the same answer, except it would be x equals negative square root of 3 divided by 2. Now, what's the difference when we get to this step? Well, if you have your unknown or your variable within a trig function, or said that, let me use proper vocabulary. If your domain, your unknown domain is inside of a trig function and the range is out here, what you can do is take an inverse, because an inverse substitutes the domain for the range. So if I take an inverse here, what's going to happen is the sine inverse, so these 2 will switch places, will be visually how it appears. But basically, I've exchanged my domain and range. That's really what I've had. I've substituted the domain and the range. And I find out that the sine inverse of negative square root of 3 over 2 will be x. And so now I'm going to open up this formula chart. For you, it's this 3rd link right there. For me, I'm just going to copy this picture up just like that, so we can see one nice and clear. And so here is my unit circle. And what we're going to do is we're going to identify where the sine value would be negative, the sine of some angle would be negative square root of 3/2. And so as by way of reminder, each of these points on the outside of the unit circle come in the coordinate pair cosine, comma sine, or x divided by h, comma y divided by h. So as I look around, I'm looking for negative square root of 3/2. Well, you won't see it on the top half of this unit circle because that's where we have positive y values. This is the y-axis, and these all have positive y values. So it's going to be down here. And so I'm looking for negative square root of 3/2. It appears to me that I'm going to find that right here in this location and this location. So I'm going to circle those two up, which means my solutions, there's one, there's a negative square root of 3/2. This comes from the angle 4π/3, and this one comes at 5π/3. So we determined that the solutions would be at 4π/3 and 5π/3. Now you might be wondering, why am I not writing them one answer comma the other answer? Well, that's because this little instruction, it says for all values of x. What that means is, since sine is, or this sine, let me point at the original sine function, is periodic, that means the values repeat if you go around a full circle. Well, a full circle is represented by 2π. And I will put in a 2 in pi, meaning you can go around an infinite number of times, but as long as you're making full circles, you will get a correct solution. So I'm going to put this, and then I'll say as long as n is an integer. So it has to be a full circle. It can't be like half a circle or 0.7 of a circle. It's got to be a full circle, which means 2π times an integer. These would be all solutions. Now I mentioned to open up a graph earlier. I'm just going to go to a blank graph right now, and I will show you this visually. So here's the equation. Whoops, I forgot the 2. 2 sine x plus square root 3 sqrt 3 equals 0. And if I type in y equals this left side of the equation, and I type in y equals the right side of the equation, which is 0, I should get all the solutions. This is where these graphs intersect. So the first two that occur from on the positive side, so starting at 0 of my domain and moving towards the right, the first two answers I see are this one here. That's 4π/3. It's the first time the blue and the green intersect with the red here, 4π/3. And the next is 5π/3. All the other ones are what we call coterminals. So they're kind of like repeated answers, even though the values are going to look different. That says 10π/3. Where do I get 10π/3? Well, if n is 1, you have 2 times 1, which is 2 times pi. So you're adding 2π. Because I had to get a common denominator, you'd multiply top and bottom by 3. And so really what I'd be adding is 6π/3. 4π/3 plus 6π/3 gives us 10π/3. Just the same here. 5π/3 plus this becomes 6π/3 gives us 11π/3. And that's how the answers repeat. I showed you this visually last class by using a slider. How did, there it is. I need a slider to come up. I don't know why I was doing that. And I want to make sure n counts as integers. Okay, so the equation is this. We're saying x equals 4π divided by 3 plus 2 n pi. And I'll copy this and give us our second answer right here. And to make this show up easier without the, you can see how if this is the original two answers, 4π/3 and 5π/3, that's these two right there. When n is 1, it's the answers 1 over to the right. N is 2, it'd be 2 over the right, 3 over the right, 4 over the right, and negative would go to the left. So you can see that's showing you each answer set. So all that is one full circle around the unit circle. That's how those appear, with 0 being representing the original 4π/3 and 5π/3 right there. Okay, so that was number 1. Number 2, it says find all solutions, this time on the interval from 0 to pi. So we're not going to do the infinite this time around. So I'm going to just take these off here for later when I check my answer. So let's solve this problem. Now this problem is a little different in that I have powers of x. So I want you to envision how you would think through solving in algebra 1, or excuse me, algebra 2, if this said 2x squared plus 3x plus 1 equals 0. So like ignore the trig functions just for a moment. And if you were to solve this, what you learned in algebra 1 is, okay, if my variables, I have different powers like this, if I have different powers of the same variable, the way to solve is by factoring. And so this is what we call quadratic. It's in the form of ax squared plus bx plus c. And we spent a lot of time earlier in the year talking about how you can factor quadratics that are rational using x method. If it wasn't rational, for the record, while I write this, you could use the quadratic formula. The x equals negative b plus or minus b squared minus 4ac all over 2a. That formula, if you remember that, you could use that for irrational factors. But we're going to assume this one's going to be rational. So my a is 2, b is 3, c is 1. A times c, 2 times 1 is 2. B is 3. So we're looking for factors of 2 that add up to 3. Well, the only factors of 2 are 1 and 2. 1 and 2. And by the way, I usually write this down as letters m and n, and I would come up with a table if they were multiple. But this one, those are the only 2 factors. They're both positive because they have to add up to 3. So now what do I do from there? I split my a terms power. So it becomes 2 cosine x plus this 1. And then again, I split the a term power. So I write it again, 2 cosine x plus 2. All that equals 0. Now I would say this is the factored form of this, but that's not entirely accurate. Because if your a is greater than 1, which it is here, then I should have an extra value of a. So notice that's an a, that's also another a. I got 2 a's. I'm only supposed to have 1 a. I mean, I know a is 2. That's confusing. Let me say this again. A is the value of 2, but I wrote it twice. So one of these has to get simplified. So it's either the front fraction that's get divided by 2, or it'll be the back fraction. I said fraction, I'm sorry, factor. To make a joke, it was the wrong F word. Not fraction, but factor. So which one gets divided? The front factor or the back factor?
The back factor.
That's right, the back. 2 can go into both terms and the back factors, so I can simplify as that. That would be cosine x plus 1 equals 0. And so now we have what you learn about in algebra 2 called the zero product property. Zero product property. If you were asked, Mr. Voorhees, do your best to summarize algebra 2 in 1 sentence, I would say to learn how to solve equations using the zero product property. That would be my summary. Now, algebra 2 teachers might argue with that, but that's my summary. And you know what? The culture we live in, if that's what I want to say it is, that's what I get to do. That's the way it works these days. No one's wrong anymore, right? Catch that? No one's wrong anymore, right? Anyways, jokes aside. Let's solve this. Zero product property states that if you have 2 factors with a product of 0, the only way it's possible to get a product of 0 is that one of the 2 factors must actually equal 0. And so I will solve this. First factor set equal to 0. So if this is 0, this factor here, then sure, multiplying would give me 0. Or if this second factor is 0, then yes, multiplying by the second factor of 0 will give us a product of 0. So I have to solve each one to get all possible solutions, like the instructions said. So we subtract 1 here. So now I've turned this into algebra 1. So how would I summarize algebra 1? I don't know. I maybe solving equations without a power. Learning to do the opposite mathematical operation might be another way of saying it. That would be algebra 1. Okay, so here, now I'm looking and I see that 2 is multiplying times cosine, so I do the opposite operation, which is division. Over here, there's not much left. So what do I now have? Once I have my cosine x equals on the, over here on the left, a -1/2. On the right, I have cosine x equals -1. Now I do the good old inverse. So an inverse, what that'll do is that'll exchange or substitute my domain and my range here. We're trying to solve for the domain and we have a range value. And so when I switch that, we will have that the cosine inverse of -1/2 will produce answers. And over here, the cosine inverse of -1 would give us solutions. So I'm going to pull up this unit circle again. Large, a little too large there. I accidentally made it look like a bit of a unit ellipse, not a circle. Whoops. Okay, so we're looking for -1/2 of a cosine. So I'm looking at the x values. -1/2 means that my x-axis needs to be negative, so the left side. I see a -1/2 there. I see a -1/2 here. So it looks like I pointed at the wrong location. That needs to be 2 pi over 3. So we have 2 pi over 3, we have 4 pi over 3, and then over here, cosine of -1, there's only one of those. It's right there. That's at pi. So if I were going to write my answers in order, and we're only going to 2 pi here, and not even including 2 pi. So we're not even going to go around a full circle. We'll stop right there at the edge. Out of here, we had 3 solutions. Going in order, 2 pi over 3 would be the first. 1 pi is the second solution, and the last answer would be 4 pi over 3. If this did not have the domain restriction there, then you would do the plus 2n pi on each of these. So let's now check our work. I come over here, and I'm going to follow the same concept that I did a second ago. I'm going to graph the entire equation here in Desmos. 2 cosine squared x plus 3 cosine x plus 1 equals 0. I will copy the left side of the equation. And I have the right side copy. Now I'm only going to be looking on the interval from 0 to 2 pi. So you can do a domain restriction by doing this little squiggly there. That's a shift bracket. And I'm restricting the domain. Interval refers to domain values. So I'm going to go 0. That bracket means it can be equal to, so less than or equal to x, which is less than 2 pi, 2 pi. Let me extend this a little bit further so you can see the whole equation. There it is. And now I'm going to copy this restriction to each of these 3 equations. What that'll do is it'll limit where my answers are. As you can see, 2 of these appear correctly on the calculator, 2 pi over 3, 4 pi over 3. For some reason, that pi is not showing. I don't know why, what the programming issue is, but that should have a vertical line going through it. I think if I take away this, no, it's not appearing still. Not sure why that's not appearing, but we do see that that is an answer. The graphs are intersecting. So there's like some type of programming error that Desmos needs to be alerted to for why that's not working. But that is the correct solution. We have 3 answers here. As you can see, 3 intersections in those graphs. All right. Number 3. It says solve for sine theta minus 1 equals 2 sine theta. So again, if I were going to treat this like algebra 1 or exchange the trig function and just treat it for a second as a theta, I would just say I have 4 theta minus 1 equals 2 theta. So they're both sine. So that's kind of the idea. So what would I do in algebra 1 if I had that is I would combine my like terms. So I'm going to do the same here. And subtract 2 sine theta from both sides of this equation. And so 4 sine thetas minus 2 sine thetas is 2 sine thetas minus 1 equals 0. And since I don't have any powers, I can go through my algebra 1 skills of just isolating the variable by performing the opposite operation. So 2 sine theta equals positive 1. Divide both sides by 2 since this 2 is multiplying. So I have sine theta equals 1/2. Or once I conduct my inverse here, I'll substitute our unknown domain for the known range value. We'll say the sine inverse of 1/2 should give us that domain value of x that we were looking for. So I'll pull up a unit circle again. I need to just copy this keep it smaller so I don't have to keep doing this. Here we go. Let me copy it one more time. All right, now I can just paste it in the future. Now we're looking for sine, which is a y value of 1/2. So I'm looking on the y values for 1/2. That means it's going to be on the upper side. This circle here is a sine value, a y value of 1/2. Comes from pi over 6. And I have another one right here. Comes from 5 pi over 6. Because this says for all values of theta, there's no restriction. This answer would need to have the plus 2 in pi. So I'm going to have pi over 6 plus 2 in pi. And I will also have the solution set of everything 5 pi over 6 and its coterminals. So that's 5 pi over 6, the original answer, plus coterminals, which would be 2 in pi. That's all coterminal values. This is true when n is an integer. Let's check that answer out. Here we have 4 sine. I'm going to use x. Here I'm going to substitute x in. Equals 2 sine x. Notice I graphed the original equation as given. I'm going to delete that. So now I come to the second equation. I'm going to type the left side, 4 sine x minus 1. Again, I'm going to remove the restriction. And then 2 sine x. We see all these different solutions. Let's check ours. We're saying it's going to be pi over 6. Oops, pi over 6. And we're saying it's going to be 5 pi over 6. And let me turn that back on. And so this is saying the first two solutions are here and here. I agree. It looks like it. Those are the first two solutions that are occurring. This 2 in pi will give us all coterminals. So if I change into 1, this purple should jump from these two solutions to these next two solutions. Let's check it. So you can see, yep. And then the n is 2. Yep, that shows you each periodic solution set, if you will. So we did do that correctly. Now I've given an extra one here to how to solve this. And we could use the calculator. But one thing I want to go through is sometimes with trig, I've listed off that spot oil so many times, but sometimes there's one that just doesn't seem to fit into spot oil. This is my little acronym. It's not just a good rule always to follow. It's just kind of an idea to get you started. But as I look at this one, I can say, okay, can I simplify? No. And this is kind of like having two variables. I have x plus y, if you will, equals 1. And you could be going, all right, well, I can't exactly solve this because one's going to be dependent upon the other, whichever one you want to call independent. So normally we say x is independent and y depends on x. That's normal vocabulary that we've learned all of our lives, or at least since we've had x's and y's. Here I am, kind of in that same scenario. But with trigonometry, that's not always the case. So on this problem, what's a little tricky is I can't simplify. I don't have any Pythagorean. I don't have an opposite denominator to do the conjugate with. I cannot transform. There are already sines and cosines, so there's no point transforming them. And then other identities we learn are cofunction and even and odd, which have nothing to do with this problem. So what do I do if those don't work? Well, honestly, you can just try to play around and solve things. But I happen to know on this one what we need to do, that sine and cosine are related with the value 1 using the Pythagorean identity if these are squared. So the first thing I want to do is try to get them squared. And if you are going to square something mathematically, you have to square the entire left side of the equation and the entire right side to keep it equal. It's not like square each item like a distribution. That's not how it works. You have to square the entire side at once, which means I have to do a FOIL here. What do I say? That means first times first. Let me just write it out so you can see. I'm going to have to multiply out all of that. And on this right side, it's just 1 times 1, which is 1. So I'll distribute here. Sine times sine is sine squared. So I'm doing FOIL. Use a little gimmick Mr. Treacy wouldn't like, but it does help us see what's happening. So sine times sine is sine squared. Then you'd have a sine times cosine, which is a sine x cos x. We would have another sine x cos x. And then finally, a cosine squared. Cos times cos is cosine squared. That's cos x times cos x is cosine squared x. All that would equal 1. So that was the FOIL right there. Okay, now what do I know from my Pythagorean identities? Let me go over here and show you. For my Pythagorean identities, we can see, here it is, Pythagorean identities, that sine squared plus cosine squared equals 1. Well, how does that play in on this problem? Well, I notice that over here I have sine squared and cosine squared. That happens to equal 1. So you can honestly just separate all that, but I'll go one step at a time. If I take out the sine squared and cosine squared, sine squared plus cosine squared, I could substitute a 1 in its place. And here I have one sine cos plus another sine cos. I have 2 sine coses or sine x cos x. So I have 2 of those. And then that sine squared plus cosine squared is 1. So that was the Pythagorean identity, and this was algebra. Pythagorean identity, and this was a little algebra. Now I'll subtract 1 from both sides, and that's what I was saying, that ultimately if I wanted to, I could have taken out that 1, could have just said, oh, that's the Pythagorean identity, sine squared plus cosine squared equals 1, and removed all 3. And we would have still got the same thing here. So now I have 2 sine x cos x equals 0. Go to solve this, I divide by my 2. And at this stage, what we found out is sine x plus cosine x equaled 1. And guess what? Sine x times cos x equals 0. Now I can do my zero product property, which states any two factors are multiplying with a product of 0. It means that one of those two factors has to equal 0. So either sine x equals 0 or cosine x equals 0. Stated another way, sine inverse of 0 equals x, or cosine inverse of 0 equals x. So now we look on our unit circle. So we're looking for inverse values of 0, both x and y. So there's going to be a lot of them. Notice here I have that's a sine inverse of 0. That comes from 0. Go around. Here's a cosine inverse of 0. That comes from pi over 2. Here's another one at pi. And there's one more. So it looks like 4 answers. It looks like 4 answers on the interval 0 to 2 pi, but we're going to find out that's not actually true. Because whenever you square a problem that's not originally squared like this, we can, and if you can see my fingers, I'm doing quote marks. We can create fake solutions, what's actually called extraneous solutions. Some of these solutions might not be real. We could have doubled the amount of actual solutions by squaring, because we introduced the square. It wasn't originally there. When you do that, you can actually double your potential answer. So let's check out and see if these are correct here. I'm going to go to the original graph. Sine x plus cos x and set that equal to 1. We have sine x plus cos x and then 1 right here. Now to limit our domain, 0 is less than or equal to x, which is less than 2 pi. I should have saved that somewhere, so I could have just pasted it really fast. Let me just put it down there. That way later if I need to copy it, I can. So we're looking for our solutions on here, and I'm looking on this graph. There should be, it looks like there's an answer here that the graphs are intersecting. Again, I don't know why it's not showing vertical lines everywhere. That's an answer solution at 0. We have another one. No, those aren't all matching. All 3 should be matching out at the same spot. Well, at least the blue and the green should be intersecting. There's another value. And then at 2 pi, it looks like we would have a solution, but 2 pi doesn't count. So we're only having these 2 solutions. Now, did I type this in correctly?
I was going to ask Mr. Voorhees, why is there a 4 on here?
There we go. Let's try that again. We have the answer 0. We have pi over 2. And then if we went all the way around, we would have 2 pi, but notice it's not even clickable. Well, maybe I froze it. It's not clickable because I eliminated the graph. I did not include 2 pi. So it appears to me that there are only 2 good answers, these 2. 0 and pi over 2, which means on this particular problem, this is very similar to a problem I worked last class. This one's extraneous, and this one's extraneous. Because when you plug them back in without the square, the math would not work out right. So this only has two good solutions, 0 and pi over 2. I don't have to do the plus 2n pi because of this particular problem, our domain is only on the unit circle 2 pi. Let's find all the solutions of 4 cosine squared equals 5 minus 4 sine x. Okay, and I'm going to write up here, spot oil, our technique we've been using. Now, the one thing that's a little tricky on this one is if you think in terms of like algebra, this is 4 cosine squared, so it's kind of like 4x squared equals 5 minus, and now we have 4 sine x, so we switch trig functions. It's kind of like saying 4y. And so it's a little bit tricky to figure this out. What we need to do is to get the common trig function. So what I'm actually going to do is I'm going to use a Pythagorean because I know sine and cosine are connected specifically when cosine is squared like this. So when I go over to my formula chart here, I want you to see on the Pythagorean identity that cosine squared, if you do a little mental manipulation, is equal to 1 minus sine squared. Now how did I get that? Since right now sine squared is being added to cosine squared, if you try to get cosine squared isolated, you would have to subtract the sine squared. So it would be 1 minus sine squared. So that's what I'm going to do first on this problem. So I'm going to say, well, what if we treated that cosine squared as 1 minus sine squared x and set that equal to 5 minus 4 sine x. Now we'll distribute this. And that right there was the Pythagorean identity. So I have 4 minus 4 sine squared x equals 5 minus 4 sine x. And so now I have the problem, and it's quadratic. I have the same trig function. I have squared, a power of 1, and just a constant values. So I'm going to get everything on the same side. I don't like dealing with negatives, so I'm going to move that to the right. So basically what I'm going to do here is I'm going to add 4 sine squared to both sides of this equation. And I'm also going to subtract 4. Now I should have put that subtract 4 right there. Let me see if I can. I can't separate it. Oh, there we can. Now I can. It heard me talking. Okay, I'm going to write that over here and take this over here. Okay. So that's basically what I'm going to be doing here. So let's see what happens here. And that goes away. This goes away. And I'm going to reorder it in the normal order where we have the squared terms first. So I'll have 0 equals 4 sine squared minus 4 sine x plus 1. And I will do the x method here. A times c, where my a is 4, my b is negative 4, my c is 1. And we're going to try to find two numbers that will multiply to be 4, but when added equal negative 4. So, little t-chart here. There are two options. We could be working with the numbers 1 and 4, or we could be working with 2 and 2. Now I want you to think about multiplying to get a positive 4, but adding to be a negative 4. The only way I think we can do it is with two negatives. So it'd be negative 2 times negative 2. Those are two numbers. So what I do, I split this power. And so I'm going to have 4 sine x minus 2. And then over here, another 4 sine x minus 2. Notice I should only have one value of 4. Here I have 2. I have an extra value of a. And so normally this means I need to divide by 4, but neither factor can be divided by 4. But what I can do instead on this one is instead of dividing one factor by 4, I can actually divide both factors by 2, and which is equivalent. Because 2 times 2 is 4. So I'm doing I'm simplifying both of these. And we'll find out, by the way, this was 0 on the other end over here. That's a 0. So let's say we now have the actual factored term. I have 2 sine x minus 1, and this would be squared. It happens twice, just the same thing twice, equals 0. So I could go through and now solve this. Let me extend my page just a little bit here. Next step, just get rid of a square. I would square root. Normally it comes with a plus or minus, but plus or minus 0 is just 0. So I have 0 equals 2 sine x minus 1. I now need to add 1 to both sides. So 1 equals 2 sine x. And then I would divide by 2. And so 1/2 equals sine x. Or when I do the inverse here, x will equal the sine inverse of 1/2. Let's get a unit circle here. Let me find one. Hang on one second. There we go, finally. So sine inverse of 1/2 happens twice. You're looking for the 1/2. Here it is in the place of y. Happens twice. It happens at pi over 6 and over here at 5 pi over 6. So it appears to me that there might be two answers, pi over 6 being the first, 5 pi over 6 being the second. Now that was a lot of work. Let's check and make sure our work is accurate. We can do that by graphing. And so I'm going to make sure I'm in radian mode here. Yeah, radian. Okay, so I'll type in the equation exactly as it was given for cosine squared x equals 5 minus 4 sine x. Okay, it doesn't seem like that's wanting to cooperate. Let me put a parenthesis just to make sure. And parenthesis there. So that's not wanting to cooperate with us. But I can copy the left side, and what I can do is I can say y equals the left, and then I can take the right side and say y equals the right. And the solutions should be anywhere between, it says 0 and 2 pi. So 0 is less than or equal to x, which is less than 2 pi, because interval means like domain values. And I'm going to restrict this one's domain as well, and that one in case they ever update it to fix it. So I'm looking for solutions here. We got pi over 6. So these graphs to me look like they should be intersecting right in there, although the point's not showing up. This one is, let me make sure I type this in correctly here. 4 cosine squared x and 5 minus 4 sine x. Yeah, it's strange how these solutions, how they're not really coming up cooperating. We think the answer should be at pi over 6, x equals pi divided by 6. There it is, right there. And we think the other answer should be at 5 pi over 6, 5 pi divided by 6, right there. And you can see those two answers do look good. They're right when those graphs are intersecting. So we did do that one correctly. All right, let's talk about verifying or proving a cofunction. We learned this cofunction on lesson 5.1, that cosine of a negative angle equals cosine of just the positive angle. And let me show you why that's true. Let's think about this in terms of cosine of negative theta being the same thing as 0 degrees, or just 0 in radians, minus theta. Like as a difference. If we did that and I look over at my formulas, what I find out this is the cosine of 0, I'll use radians, cosine of 0 times the cosine of theta plus sine of 0 sine of theta. Okay, now I want to paste here, I have a unit circle. And if we go to the radians of 0, let's see what these values are. At 0 radians, cosine is 1, which equals 1 times cosine theta plus, now the sine of it is 0. 0 times sine of theta. Well, 0 times anything is nothing. So basically we find out this equals cosine theta. And so we verified that this is true. So I use right there the sum and difference identity. That's actually the difference identity, I should say. It's the cosine difference identity. That's the cosine difference identity. And then right here, I did a little algebra. Those are my steps to prove that was true. Now I have one for you to try. And now let's look at example 6 here. Let's look at, they call this a reduction. We called it a cofunction earlier in the year. And so we had this relationship. Let's prove that it's true. So cosine of pi over 2, we're going to treat this as A and this is B. What that would be equal to, so let me do it the way I was doing on lesson 5.2 in particular. Cut it in half. Say, all right, well, this is like a difference identity. So I'll say that all that's going to be equal to cosine of angle A times the cosine of angle B. And don't take the negative, just the pi over 2. And with cosine's formula, and notice the sign changes. So it would be the sine of theta times the sine of pi over 2. Okay, now I can substitute some of these values. Let me take a formula chart value. Whoops. Here, what I can do is pi over 2. Here's pi over 2. The cosine of that is 0. So basically I have cosine theta times 0 plus the sine of that's 1. 1 times the sine of pi over 2. I wrote that opposite order, I'm sorry. Sine theta times 1. There we go. That's the correct order. That would cancel out. Let me change colors. That would cancel out because 0 times anything is 0. And so you're just left with sine theta. So I did algebra on this last step. And this was the sum and difference identity. I guess it's subtraction, so I should say the cosine difference identity. And you can see it all works out. Or let's try this one. Tangent of x minus 360 equals tangent of x. So this is just checking to see if something's coterminal. Coterminal. Okay, so using our formula that we have for tangent, if that's subtraction, we have that that's going to be equal to tangent of angle A. So here's A, B, minus tangent, oops, sorry, right sign, tangent 360 over 1 plus tangent x, tangent 360. So that is the tangent difference identity. Right there. All right, now let's get our formula chart here so we can do some algebra. 360 is also right here at 360, which is 0 over 1. So what I have is tangent x minus 0 divided by 1 over 1 plus tangent x times 0 over 1. Now multiplying by 0 cancels all that out. And so you're left with tangent x over 1, which simply put is tangent. And all that was doing was algebra right there. And that would be your solution. So now I have this one for you to try. Let's take a look at example 7 here. It says solve the trigonometric equation. So we have all of this, and could we do this by graphing? You bet. But I want to try to do this by hand first. So I have a sum, a sign that's a sum, and a sign that's a difference. And by recall, or we can just look over here at the formula. So I'm going to first rewrite this and say that this is going to be, let's call this A1. I'm going to call this A1, B1. So when you hear me say the English, you know what I'm talking about. A2, B2. That's what I'm talking about. So for the sine of A1 plus B1, I'm going to use this formula, which means I'm going to have sine of x times the cosine of pi over 4b. And that's going to be plus cosine x times sine of b, pi over 4. Now I'm going to subtract. With subtraction, it's a little different because you need to make sure we distribute this. So I want to put it in these big brackets here. I'm now going to subtract, and I'm using the difference formula now. So it'll be sine A, so sine x times cosine b, cosine. My second angle, notice I treat it as the positive. I don't distribute the negative, I just treat it as the positive. Pi over 4 minus cosine A, cos x, sine b, sine pi over 4. So we will distribute this negative through here. And what we'll find out is I have a sine x cosine pi over 4 plus a cosine x sine pi over 4 minus a sine x cosine pi over 4 plus two negatives to make a positive cos x sine pi over 4. And all this has to equal 0. All right, and as I look on here, I notice that I have a positive sine x cosine pi over 4 and a negative sine x cosine pi over 4. And I have two of these. So I have two cos x's sine pi over 4s. And now I'm going to get a unit circle real quick and say I know the value to sine pi over 4. Here's pi over 4 right here, and the sine of that is square root of 2 over 2, so I can substitute. So I have 2 cos x times square root of 2 over 2 is going to equal 0. And I can see that this 2 and this 2 will cancel each other out. That's gone. And I could actually divide by the square root of 2. And so these are now gone. And so we find that cosine x is equal to 0, or inverse time. If I take an inverse here, I can establish that cosine inverse of 0 equals x. So you look on here for when x is 0, you have two spots. So it says on the interval from 0 to 2 pi, so it'll just be those two solutions. So it looks like it's going to be pi over 2 and 3 pi over 2. Now, before I box that up, let's check on the calculator to see, or the graph, to see if that's correct. So I'm going to have sine x plus pi over 4 minus sine x minus pi over 4. I'm going to check my mode, make sure I'm in radians, good. And this needs to equal 0. And so now I'm going to copy this left side, and I'll copy the right side of y equals 0. And we could do the domain restriction as well, from 0 less than to equal to x to less than 2 pi. I can copy this on each of these three. So this has two solutions. It has pi over 2, 3 pi over 2. I agree. It's the exact math we got. Now you have one for yourself to try. So that's how you can solve with the sum and difference formula. So you go ahead and try this one. I'll put, no, that's not what I want to do. I want to copy this for you. Copy. And I'll put up the formula chart as well. You can pause the video and solve. Now let's take a look at this ACP problem. It says Jill measured the angle of elevation to the top of the flagpole to be 31 degrees. That's right here. And elevation just means the angle's looking up. If you're wondering what that vocabulary means, that's what that means. Jill moves forward 126 feet. That's why there's an arrow here. They move this way. Passing the flagpole, she looks back, and the measure of angle of elevation now is 43 degrees. That's looking up. What is the height of the flagpole? That's what we're trying to solve here, to the nearest tenth of a foot. Now, we can't solve as the triangle on the left or the triangle on the right, because for any triangle, you have to have three pieces of information. Right now, I have it for the triangle on the right here. I have a right angle and the angle. On the left, I have a right angle and an angle, but neither one of them do I have this bottom length. That's for the whole circle. So this is going to be one that's in two steps that I need to solve either using law of cosines or sines to get another piece of information on the large circle or large triangle to then solve one half of the triangle. So what I see I can do here really quickly is that this angle right there from there will be equal to 180 minus 31 minus 43. So basically 180 minus 74. What is that? 104, I think. 180 minus 31 minus 43. 106, sorry. 106. So 106 degrees goes there. Now I can see, oh, I have a completed set. So I could do the law of sines. So when I go to my Desmos graphs, I'm going to find the law of sines. And what I know I have is that I have this completed set here of sine 106 over the length 126. And I could set this equal to either of the two. I'll just use sine 31. Sine 31, and I'll just call this R for the right side. So sine 31 over R. We could cross multiply that and divide it, but I'm just going to use the calculator. So angle A is 106. The length is 126. Angle B is 31. Side length B is unknown. This says the answer is going to be 67.5, 67.51. To be a little bit more precise, let's say 65.51. So I come over here and I'm going to erase that and just say 65.51 is that length. No, 67, sorry. 67.51. And so now that I have that, I can come back and solve this using this half of the triangle. And I can just stick with the law of sines if I want, since I'm right there. Say we now have a completed set, and I'll use this one. So now I'll come back. So we got here that that is equal to 67.51. And now I will say that sine of, and use this completed set, sine of 90 degrees over 67.51 will equal sine 43 degrees, whoops, 43 over the height. And I'll do this calculation and we should have our solution. 90 over 67.51 sine 43 over x. The solution here, it says is 46.04. That says to the nearest tenth of a foot would be 46.0. So you could just say 46, or you can do the 0.0 if you prefer, and that would be your solution. And that's now a wrap for lesson 5-4.